right, good morning. Hope everybody had a nice holiday weekend. I know you guys at least studied chemistry one time while you were off. Okay, it's been a whole week. So obviously no lab today, so you got lab next week, I believe. So, all right. Justin Anderson. Heath Bell. Alex Bennett. Alex Kumar. Mariah. Tyler Cook. Jesse Davis. Justin Davis. Slowly trying to learn you guys' names. Yolanda. Jordan Elledge. Jordan. Robert Feldman. Tiffany Kennedy. Andy. Daniel Lee. Jamison Maxwell. Joey Motter. Or Motor. Okay. You're Jesse, right? Jesse Davis. Okay. David Peterson. Hayden Phillips. Alicio. Eric Reeves. Dylan Reiser. Dylan. Wesley. Russell. Josiah Scott. Brittany Skinner. Clayton Strickland. Jennifer. Jesse Thompson. Taylor Thompson. Taylor. Darius Troop. Darius. Anderson Young. All right, go back just in case anybody came in. Alex. Jordan. Robert. Joey. David. Dylan. David Peterson. Okay. I said Daniel Lee, but I think. Okay. Dylan Reiser. Did somebody say here? Taylor Thompson and Darius. Okay. Matthew Abernathy. Tina. Jacob. Bobo. Sorry, I need to do the last. Emily Boucher. Taylor Bowling. Caitlin Davis. Scott Graham. Brock Hester. Andrew Jordan. Andrew Cody. Leah Lauterbach. Jake LeCroy. Justin Lee. Damian Moorhead. Damian. Katie Moss. Ryan Patterson. China Ponter. Leon Rathburn. Wesley Sajouse. Okay. Denzel Sears. Hunter Shell. Stephanie Simmons. Stephanie. Tyler Sims. Miranda Stewart. Tevin Terry. Mason Throneberry. Nick Waddell. Jacob Young. Okay. And Joey just came in. Okay, did I miss anybody? Did I? Hope I got it. Okay, just for a second, we're going to review the last couple things that we talked about. Be sure everybody remembers this. Okay, we were talking about electrons and the fact that electrons aren't just randomly spaced out around the nucleus. Okay, so we had previously talked about that our protons and our neutrons are in the nucleus and that we can look at the periodic table and we can look at the atomic number and we know the number of protons. Okay, if we have a neutral element, we also know the number of electrons. So that proton atomic number would be the same. Okay, so then we started looking at electrons and the fact that we can look at the probability of finding an electron around the nucleus. Okay, does anybody remember what our electrons reside in, or what mathematical function do they reside in? Remember, it's a mathematical function. Good try. Okay, what do the electrons reside in? Orbitals, okay? And so we looked at 4 different types, but we're mainly going to be looking at 3 of them. Okay, so we looked at s orbitals. Okay, the s was that sphere-looking orbital. Okay, remember, it is a mathematical operation. Okay, it's not an actual seat for electrons. Okay, and each orbital can hold how many electrons? Okay, but each orbital by itself can only hold 2. Okay, so if we have one s orbital, it can hold 2. Okay, if we have p orbitals, there are 3 p orbitals, p, x, y, and z, and each of which can hold 2. So p orbitals can hold 6. Okay, and then for our d orbitals, we have 5. We have 5 different d orbitals. They were pretty hard to draw. Okay, and so we can hold up to 10 electrons in our d orbitals. Okay, and then we have f orbitals also, and they hold up to 14. There's 7 orbitals for those. Okay, so what we're going to do now is we're going to write an electron configuration. Basically, we're going to be bookkeeping electrons for an atom, and we're going to even look at ions. Okay, so you definitely need your periodic table. Okay, I'm going to try to hold this guy up for a little bit, but I won't be able to hold it up the whole time. Okay, we're going to look at electron configurations, and then we're also going to draw what are called orbital diagrams. So if you're working on your quiz and you got to the last 2 and you're going, I don't know what this is, we didn't learn this, that's because we're learning it today. So you should be able to finish the quiz after today. Okay, this takes a little bit of practice, but some of you may have had chemistry before, or you've already done this. So, but for those of you that haven't, it takes practice. It takes a few minutes. Most students kind of look at me like, I don't get this. But by the end of the class, hopefully you will get it. It's actually one of the highest graded parts of the exam because students actually think, oh, okay, I don't know if I get this, and they really work hard to try to understand it. So it ends up being something that sticks with the students, I feel like. So, okay, so we're going to bookkeep our electrons. So first we got to talk about some rules. Okay, this isn't going to make much sense until we start actually putting this into practice. Okay, so just kind of absorb the rules. All right. We're going to add the necessary number of electrons into orbitals. Okay, so the necessary number depends on what atom we're looking at. Okay, and we're going to add them in a way that gives the lowest total energy. Okay, remember our atoms, our elements, they want to be stable. They want to be in the lowest energy possible. Okay, and this is known as the Aufbau principle. 2 electrons in the same orbital are going to have opposite spins. Okay, so we're going to just draw a line for an orbital. We're not going to draw, all the P's and D's and all that. Okay, and so if we have a situation where we have 2 electrons in one orbital, which is going to happen quite a bit, okay, they're going to have opposite spins. Okay, and so how we would draw this is we designate the electrons with arrows. So say we have an orbital. Okay, I'm not going to designate which orbital. We would have 1 electron up and 1 electron down. Okay? The reason for this is that electrons have the same charge, right? They're 2 negatively charged electrons. So the way I think about it is they're going to want to repel. They don't really want to be in that same orbital together. Okay? So one of them is going to spin flip and be like this. Okay? So it'd be lower in energy if they have opposite spins. Okay, Hund's rule tells us that electrons occupy all of the orbitals of a given subshell singly before they pair. Okay, so if we have 3 p orbitals and we have 3 electrons that need to go into those orbitals, we're going to put 1 in this orbital, one in this one, and then one in this one. Okay, we're not going to pair them first and then put one here. Okay, does that make sense? They'd rather be by themselves in an orbital. They don't want a roommate, if you want to think of it that way. They'd rather be by themselves. Okay. When I was learning this, and it wasn't that long ago, believe it or not, but my book did not go into detail about the periodic table and how I could use it to place electrons into orbitals. So I sat there and all I did was just memorize, okay, the 1s2, 2s2, 3s2. And it soon left me because when you just memorize things, they don't stick with you. Okay, so we're going to look at how we can use the periodic table to do the same thing. And you're basically just going to read the periodic table from left to right. And you're going to see that not only the periodic table does it have groups that have similar trends, and it has atomic numbers, and it has all these different wonderful things that we've already looked at. It also, by going in order of increasing atomic number, we end up being able to look at it if we know how, and we can put electrons into the orbitals from lowest to highest energy, as long as we know how to read the periodic table. Okay, so this is why the periodic table is a chemist's best friend. Not the only reason, but one of the reasons. We use it all the time. Okay, but first we have to know how to break up the periodic table. Okay, we're going to have an S block. What do you think that S stands for? S orbital. And we're going to have a P block over here. Stands for P orbitals. Okay, we have a D block. This is your transition metal area. Okay, and then we have F block. We're not going to get down into those, but there is an F block. Okay, so first thing I want to show you is if we look at the S block and we count over. So we've just got our group 1 and 2. That's our S block. Okay. So if we were to read from left to right and we were to be thinking in the effect of electrons, okay, and we are going to move from left to right. So if we're coming up with the electron configuration for, I don't know, let's say, you can't really see it here, but 7, so for nitrogen, okay? And we're going to move along starting at the very top line, just like you read a book, and we're going to read from left to right, then go down to the second line and read from left to right. Okay, does anybody remember what does the period number tell you with respect to electrons? Okay, each period number corresponds to the shell, the energy level. Okay, so the first period, we're in the first energy level around the nucleus. Okay, the second period, we're in the second energy level around the nucleus. Okay, so we're going to read from left to right. Okay, but we're going to first just look at why this works. Okay. So we have an S block that's sticking up here. Okay, and if we're moving over, we're thinking of counting electrons. So if we're counting and you're in the S block, then you're considering that there's an electron in the S orbital as you're moving across. Okay, so if we count over, how many electrons could we hold in this S block? If we move from, say, 3 to 4. How many spaces do we have if we're not even looking at elements? We have 2. Okay, how many electrons does the S orbital hold? 2. Okay, let's move over to the P block. Okay, let's count across. How many spaces do we have? 1, 2, 3, 4, 5, 6. How many electrons do P orbitals hold? 6. Okay, D orbitals, right here. Count over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many electrons do the D orbitals hold? 10. Kind of getting the idea of how this is going to work? Okay. I'm not going to give you, I'll give you a periodic table, obviously, but I'm not going to give you it broken down into S, P, and D. Okay, that's something that you should be able to see. Okay. Okay, so we're going to look at the very simplest elements. I'm going to hold this up. This is really old, so it's not going to be an updated periodic table. I don't even know if it's going to hold up. But we're just going to practice first. Okay, so you've got your own if you want to look. Okay, but if we were doing hydrogen, and we're writing the configuration for hydrogen, okay, it's the first element, atomic number 1, so how many electrons are we going to show? 1. Okay, when you're writing this out, this superscript is the electrons. Okay. S is the orbital that we're in. And where does this 1 come from, you think? The orbital, the period number, right? We start at 1s1. We're always going to start there. Okay, we're going to read. I can't see this, sorry. I'm going to go over here. Okay. So the electron configuration for hydrogen is 1 because we're in period 1, S because we're in the S block, and 1 because we only have 1 electron. Okay? Sometimes you see, like I said, helium will be over here with this, or this will be over here. But you're always starting out, if you're going to end up passing by helium, your first orbital is 1s2. Okay? So if we look at helium, we would say, okay, we went through 1s1, but now we're at 1s2. So the electron configuration for helium is what, S2. Okay. We're just going to keep practicing here. Okay, let me find another one. Okay, let's go to boron. Okay, we got to start up at the top. I'll show you a shorthand version later. Don't learn the full thing right now. Okay, so we're going to go across. So we got to get all the way to boron. So everything we pass through, we've got to account for. Okay, so we've got 1s1, 1s2. So we would write out. Go ahead and write out for boron. 1s2. Okay, that's your first orbital that we go through, the lowest energy orbital. Okay, then we're going to come down to here. We're going to come down to the second period. And we're going to pass through what? 2s2, right? Because we're passing by each of them. Okay, so then we're going to move on over. See how we have this space here? We're going to move all the way over to boron. Okay, but what block are we in now? P. Okay, we're still in the second energy level, right? We're still in 2. So we would write 2p1. 1. Yeah, it starts over. So you only have 2 there. You start over. So this would be 2p2, 2p3, 2p4, 5, and 6. Okay. We'll do another one here. Okay, so here are some examples that we're going to do. But let's look at fluorine first. Okay. So if we go through, we've got 1s2. Okay, everybody see that? Okay, we go down to the second energy level. So we've got 2s2. So I've got that up here. Okay, we're going to fluorine. Okay, fluorine is right here. So now we're in the 2p block, and we count over 1, 2, 3, 4, 5. 2p5. That is the electron configuration for fluorine. Okay, so let's do another one together. Let's do argon. Okay? All right, so where do we start? 1s2, come down to 2, 2s2, and then we move over to 2p, and now we're going to fill up all 6, right? So we'd have 2p6. Okay, so 1s2, 2s2, 2p6. Okay, then we're going to come down to 3s2. Okay. And now if we go over, what are we going to end with? 1, 2, 3, 4, 5, 6. 3p6. Yes, we haven't put them into the diagrams yet. I'm going to show that, but yeah, you would count up your arrows. For these electrons, you would just, put up the superscript. But that's a great point. When you finish, if you add up your superscript, so if you add up 2, 2, and 5, you should get the correct number of electrons for the element that you're trying to find the configuration for. Okay, so for fluorine, it should be 9, and we have an atomic number of 9, which means we have 9 electrons. Okay. There is one just small variation, and just have to this is kind of just memorizing it. But when you get down to, let me go back to this real quick. Some of you may have noticed this, maybe not. But if we go back to our chart here, Okay. So we get down to the fourth period here, and we should be at energy level 4. Okay. But do you notice how when we hit here, we are in 3D? Okay. It drops one energy level. Okay. So it's not 4D. You start with 3D. And that's just something you just have to kind of get used to with practice, and just remember that these D orbitals are actually in the 3rd energy level. Okay, that's what that 3 means, right? But they're higher in energy. Okay, so kind of hard to see. Okay, but that's why 4S comes first and then 3D, because that's the order from lowest to highest energy. Okay, that's what's unique about the periodic table, is that it puts them in order from lowest to highest energy. Okay, I mentioned this one time, but what electrons do you think are the highest in energy? Which electrons? When you're looking at any atom, think the inner shell or the outer shell? The outer shell, exactly. So that's what we're going to be looking at later when we're looking at bonding, because those outer shell electrons, also known as valence electrons, are what are involved in bonding. Okay, so that's going to be really important for us later. Okay, so let's finish out. Okay, so I want you guys to work on cobalt. Okay, so you're going to have to use your, not really rule, but remember that your D here is 3, not 4. Okay, so just go through and go ahead and do the same for iodine. So that will be kind of a long one. And then I'll show you a shortcut after you do it the long one. maybe about another minute to finish up, and we'll walk through it. Did Matthew come in? Matthew Abernathy? What about Damien? Stephanie? Stephanie come in? Alex Bennett? Jordan? Robert? Dylan? Taylor? And Darius. Okay, so let's walk through this. Just going to do it this way. Walk slowly through it. Okay. Okay, so what we're trying to find is cobalt. Okay, so how many electrons, when we add up the configuration, we add up our superscripts, how many electrons do we need to have? 27. Okay, we start just like we read a book up here. You're always going to, unless it's hydrogen, you're going to start with 1s2. Okay, so move across. 1s2. Okay, now go down to 2s2. Okay. We're going to go over here because we have this big gap, and we count 2p6. Okay? Now we're going to go down to 3. Am I in 3? There we go. Okay. 3s2. Okay? And then we're going to move over to 3. Oh, where am I? 1, 2, 3. 3p6. Okay. Now we move down to, okay, 4s2. Okay. Now we're in the D block. Okay. Our energy level, can't talk, number goes down, right? Okay, so we're 4, but this is 3. Okay, 3D. So 1, 2, 3, 4, 5, 6, and 7. Who got it? Awesome. All right. Now we've got one even further down. You'll appreciate the shortcut here in a second. Yes. Go ahead. Yeah, that's what you're going to do. It's all consistent. Okay, so we can go ahead. Let's do that instead of me going back through. Everybody seem to get this part? Okay, so we got to 4s2. Okay, so everything would be the same there. And then we would have, instead of 3d7, we're going to have 3d10. Okay, now a lot of students will accidentally keep this as a 3. Okay, it goes back to 4. It's only the D block where you move down. Okay, so now we're at 4p6. Okay, we still got to go down to here. Okay, so we're going to go back now to 5s2. Okay, so 1, 2, 3, 5. 5s2. 4. Remember, this was 3. This is 4. 4d10. Now we're back over to 5p. 1, 2, 3, 4, 5. So if you add up all your superscripts there, then you would get 53. Yes. Okay. Shortcut version. Okay. Typically for any of your row or period 1, 2, 3, you don't really need this, but let's do the shorthand for iodine. It is pretty far down the periodic table. Okay, what you do is you go back to the nearest noble gas. Okay, so if we look here, we can't just move over here, right, because we've passed our iodine. You have to go back to the nearest noble gas, which would be krypton. Okay, and so then you can do this. You can put krypton in brackets, and that means everything before it, or the configuration all the way up through krypton. Okay, so we would do that. Okay. And then we go from here and we finish it out. Okay, so we'd be what? 1, 2, 3, 4, 5. We just did this. So 5s2, 4d10, 5s2, 4d10. Okay. Any questions on this?
So it's the last number that you pass.
Yes. You have to have passed it. You can't go before it because then you would be moving ahead. Yes. I will designate if it's not. So if it's a really short one, then I don't really, so say I gave you lithium, you don't really, you know. Yeah. So you just do helium 2s1 or whatever. Yes, we're about to do that. Yep. Okay. Now we're going to put the orbitals and the electrons into what we call an orbital diagram. One of the things that's most forgotten is that what we're doing in this diagram is we're showing the lowest energy to the highest energy orbitals. Okay? So we're placing them in order from lowest to highest. Okay, but nice thing is you already know that because you use the periodic table and it's lowest to highest energy. Okay, so I'm going to show you one. So let's do fluorine. Okay, we're going to draw a diagram. Okay, this is just, I'll just leave that. So this is energy. Okay, go ahead and write it out. Okay, so we're doing this for fluorine. Okay. So what we're going to use is an orbital. Instead of drawing the different orbitals, we're just going to draw that line that I showed you earlier. So we're going to go like this, and we're going to call this the 1s orbital. It's not the 1s2, it's the 1s, because now you're going to show me, what does that 2 stand for? What's that 2? Electrons, and you're going to show me those. So another common mistake. Students put 1s2, 2s2. Okay, you're going to show me the electrons. You're not going to write it out or put the number. Okay. There's only one s orbital, so we've got to put both of the electrons in the same orbital, and they are going to be opposite spins, right, when they're in the same orbital. Okay. Next, we're going to go up to 2s orbital, and we've got 2 of these. Okay. What I like to do is keep all my s orbitals in order, all my p orbitals in order, and all of my d orbitals in order. Okay, and I'll show you what I mean by that. Every time that you draw another orbital, you need to go up in energy. Okay, a lot of students, if you're drawing really small, and I can't tell if you actually went up. So, no, you don't need to put 1s here and 1s2 on the top of the page. Okay, but you need to make it noticeable that it's going up in energy each time that you're moving up with orbitals. Okay, so our next is the 2p. Okay, we've got 3 of these. Okay, I like to put all my 1s kind of in one column, all of my p's in another, but I still went up in energy. Okay, don't do this. Okay. All right, so I've got 5 electrons that need to go into the 3p orbital. So let's call these are my 2p. We're still on the second energy level. Okay, so let's place 5 electrons. 1, 2, 3. Place them singly first, and then we go back and fill in 4 and 5. Yes? What do you mean beside each other?
Yeah, like from left to right. Like whenever I wrote it out, I did 1s2, 2s2, 2p5. Bam, bam, bam.
Okay.
The same way that the ones on the computer.
Okay. You'll have to show me what you're talking about, but the correct way that I learned and that we teach here is that you put it into this is an energy diagram. Okay? And so we need to show that each energy level we have, or orbital, is higher in energy every time that we go up. Okay, so contrary to what you may have learned, I'm not saying it's wrong or whatever, but I know this is one of the correct ways to do it. This is what I require. So. Okay, well, this is the way I teach it, so yeah. But if you show me, then I'll look at it and see, but this is the way that I've been taught, so. Okay, so let's do another one. Let's work on cobalt. Okay. Okay. Yeah, you guys can show me after class, and I'll look at it because I don't visually see what you're doing. So, okay. All right. So we came up with our energy diagram we went over the electron configuration. So we're going to place for cobalt. Yeah, let's write out again let's see, it was 1s2, 2s2, 2p6, 3s2, 3p6, and then we were 4s2 and 3d7. I'm probably going to need a little bit more room, but I'll just keep going up. Okay, then we have our 2p6. Our 3s2. Now we're going to have still going up in energy each time. So now we have our 3p. Six. I'm going to move above the words here this time. Okay, and now we have 4s. And now, especially if I had to keep going there, I still move up in energy, but I like to kind of put all of my d orbitals. So I usually put s, p, and then d. Okay, and so we have our 3d. So 1, 2, 4, 5, 6, and 7. Yes. Okay. Our d orbitals, there are 5 d orbitals, and they can hold up to 10 electrons. Just like our p has 3, our d has 5 orbitals. Okay. There are exceptions. We may not, I don't know what time it is today, but we're going to keep going, but I'm going to probably leave you with a question to think about exceptions, because that's just kind of part of it. There are always exceptions to the rules, so we look at those sometimes. Yes?
So your last 3 orbitals, like 3d7,
Yep.
all of those electrons, all of those are going to be considered valence electrons, or just that last orbital? Like, you know how you said fill up singly?
Yes.
And then the first 2 orbitals, 3d, filled up. The last 3 just have single electrons.
Yeah. Your
All valence electrons.
valence electrons is the outer shell. So these are harder. I won't do a lot with the d orbitals just because they're different. They don't follow the trends a lot of the time. But your outer shell is actually your 4 right there. So you've got your 4th energy level. But like here, so this is a good question. It's on the next slide, actually, what you're asking. So if we look at our fluorine here, okay, how many valence electrons or outer shell electrons do you think we have? Okay. Somebody says 2. Okay. Why'd you say 7? Exactly. So you have to look at, remember, your outer energy level is 2. So you have 2 in the S, and you have 2 here. So you have to look at the energy level. So you have 1, 2, 3, 4, 5, 6, 7. Okay, and this brings us to the next slide. So let me go to that. Okay. So when we have chemical reactions, we're going to talk a lot about this through the semester and bonding and different types of bonding. Okay? Atoms are going to lose, gain, or share electrons. Okay? And so we're going to kind of put in here in a second why they do this and why that they bond in the way that they do. Okay? So when we look at these diagrams, so what's the point of drawing them? Okay? We want to keep track of our electrons. And it's also going to, we can look at those diagrams and we can see how many electrons does that metal want to lose or would that nonmetal want to gain. Okay? And so we're going to be looking at the valence electrons, so what he was just talking about. These are the outermost electrons in the outer energy level, okay? And they're the most accessible. They have the greatest influence on bonding and reactivity because they're in this outer shell and they easily collide with other compounds and they share or they transfer their electrons in what we call bonds. So they make bonds with other atoms. Okay, so if we think about what I've already mentioned before, and you'll keep hearing this over and over, but metals want to lose electrons. Okay, so we're going to look at a metal here in a second and its configuration. Okay, and nonmetals want to gain electrons. Okay, because they want to be like the nearest noble gas. Okay, so let's look at this. So let's look at our diagrams and see why this is the case. Okay, before I move on, though, I forgot to say this. If you look at your group numbers, okay, for your group A elements, okay, so group 1 and 2, 3, 4, 5, 6, 7, and 8, okay, that number, whatever group they're in, is equal to the number of valence electrons, or outer shell electrons. I think that's one of the questions on your quiz. I think it is anyways. So let's say nitrogen. How many valence electrons, outer shell electrons, does it have? 5. It's in group 5. Okay, it has 7 protons. Okay, the group number indicates the number of valence electrons. Okay, and you're going to show me this. So what did we just look at? We looked at fluorine. Okay, and what was your name? What's your name? Alex. He told me that there were 7 valence electrons. Okay, our diagram showed that there were 7 valence electrons because fluorine is in group 7. Okay, so those match up. Okay. All right, so let's write out the electron configuration for magnesium. Okay, so it's got 12 protons. So it means it's got 12 electrons. Okay, so we'd have 1s2, 2s2, 2p6. We'd have 3s2. And that would be it. Okay. So if we drew this out in our orbital diagram, so this is magnesium. Okay. So if we look at our diagram here, we see that we have 2 electrons in the 3s orbital. But we know that all atoms strive to be like the noble gases. So they want to have the same electron configuration as the nearest noble gas. Okay, so if you look at your periodic table, what is the nearest noble gas to magnesium? Neon, exactly. Okay, so what's going to happen to magnesium in order for it to look like or be like electronically neon? Lose 2. Okay, so it's not a coincidence that magnesium is always a +2 ion, okay, because it wants to lose 2. It doesn't want to lose 1 or 3 or 4. It wants to lose 2. Okay, so if it loses 2, that's how we represent an ion. So we say magnesium 2+. That's the cation of the metal magnesium. Okay, if we were to write the electron configuration for this, what's going to happen here is sometimes you see it written as 3s0, but how to teach it is all you do, if you lose 2 electrons, then your outer energy level now is 2p6. Okay, so let's change our orbital diagram. Okay, and it would look like this. Okay, we're still looking at magnesium, but now it's magnesium ion. Okay, and we say that it's isoelectronic. It's electronically the same as neon. That's the term that we give this. So it electronically looks like neon. It's not neon, but it electronically looks like it. Okay, so we already looked at fluorine. We actually already drew its diagram, so we'll draw it again. So if we look at the diagram of fluorine, which you already have this drawn on your paper, I believe, and we see that we have 5 electrons in the 2p. We have 7 total valence electrons. Okay, so in our outer shell, we've got 2, 4, 6, and 7. Okay, and we look at this, and we see that our last p orbital here is missing 1 electron. Okay, so in order for fluorine to electronically look like the nearest noble gas, how many electrons would it want to gain? 1. Okay, so that's exactly what it does. So when fluorine gains an electron, it becomes fluoride with a -1 charge. And so it's going to look like this. And we would have a 2p. 6. Okay, so if we look at fluoride, it now looks like the nearest noble gas, neon, electronically. And so how many valence electrons do we have? 8. Okay, so we call this a full octet. This is kind of what atoms, they bond in this way, or they lose or gain electrons or share them. We're going to see how they do this, but based upon looking at their orbital diagram or their electron configuration, we can tell how many electrons that an atom is going to want to gain or it's going to want to lose. On this, 8 valence, you have 2 here and 6 here. Yeah, because you're in the 2nd energy level. Yeah, you have to include, that's a common mistake, is just to, yeah, you've got to go to where you have, remember that number out front corresponds to the energy level. So go out to that. Okay, so if we look at our magnesium ion, how many valence electrons do we have? 8. So you're going to see a trend with respect to metals and nonmetals. When they lose or gain the appropriate number of electrons, they're going to want to have 8, because how many do nonmetals have in their valence shell? How many valence electrons do noble gases have? 8. Okay, they're in group 8, and they have 8 valence electrons.
So if it's a minus, you go forward to your closest noble gas, or plus, you go back.
Yep, and you can think about it as, for your nonmetals, they're gaining an electron, so going forward. Or for metals, they're losing electrons or an electron to go back, if you want to think about it that way. Okay. Okay, like I said, there are exceptions. So I'm going to put one up here. You guys are awful antsy. Do y'all need more practice on this? Are y'all getting this? Y'all seem like stressed out or something. Okay. Do y'all want to practice these more? Because we can. Okay. Okay, let me show you this, because this is what I'm going to leave you with to think about. And we'll talk about it on Monday. And then we'll practice some more. Okay. All right, so you want to write this down, because you want to look at this and think about it. Okay, you've got some exceptions on the periodic table. Your book goes into, some details. I just want to, hit the high points of exceptions. I don't really go into detail with these, just because I want you guys to get what happens most of the time and understand that. Okay, but we do have a couple exceptions in our 3D orbitals. Okay, so we have an exception with chromium and copper. Okay. All right. I'm going to write out what the electron configuration is. Okay, and it's going to look a little different. Okay, that's why it's an exception. And then I want you guys to think about, don't say it out loud, we'll talk about it on Monday, and look it up, whatever you want to do. Okay, and we're going to talk about why it's an exception. Okay, and I'll give you a hint. Draw out the electron diagram or the orbital diagram, and that will help you. Okay, so for chromium, we've got, this is for chromium. For copper, okay. Yes, it's a 9, sorry. Okay, so the difference here is that 4s1, right? So that's obviously what you see there. Okay, so I'll leave you guys with this. We'll talk about it later. All right, if you want to get out, if you've got your quiz, or do you guys just want to run through a couple more, either the diagram or the configuration? Which one?
We do the diagram, so all the X's will be here and all the T's will be there and all the lights just going up.
Yeah, some people just keep going up, and it just gets so long. If you kind of put them in columns, if you have a long one, it's P's and then D's. Just be sure you're going up in energy each time. Okay, so, okay, do you guys want to, let's look at, which one were you saying? We can do it. Did you say one?
Phosphorus, 3
Okay, we'll do that one. Taken forever. Okay, we're going to do phosphorus ion, P3 minus. Wish there was an easier way to. Okay. Okay, so I'm going to give you guys a second. Okay, it can be P minus 3, 3 minus, same thing. Okay, I'm going to give you guys a second to work on it, and then we'll go over it. Okay, draw the electron configuration and the orbital diagram. Okay, real quick before we do that one, I meant to put 3D10. I had it written down. I was looking at a different one. So it should be 3D10 to match up with copper. Yeah, I was looking at nickel. I did that. So it made more sense now. Okay. Phosphorus, 3 minus. Okay, so what does that -3 charge mean? So it's gained 3 electrons, right? Okay, so if we look at the periodic table and we move over 3 electrons, what is it going to be isoelectronic with? Argon. So you're basically, when you are drawing the orbital diagram, you're going to be drawing electronically what looks like argon. Okay, so we'll go ahead and write out the electron configuration. So we've got 1s2, 2s2, 2p6, 3s2, and 3p6. You can unless I say otherwise. Yep, unless I tell you not to use the shorthand. Yep. Okay, so if we do our orbital diagram, okay, so energy is what we're looking at here. So we have 1s2, so it gains 3 electrons. It's not a coincidence. The reason that it does is because now, how many valence electrons does phosphorus have? 8, because that's what the nearest noble gas, and that means that it is more stable with 8 than it would be with just 5. Okay? All right, another one. Anybody got another one they want to do? Okay, what I'll do now is any of you that did your diagram the other way or whatever, if you want to bring those people that want to do it that way I can look at it and see if I'll accept it or not, and then any other questions you have. But we'll start with Chapter 5 on Monday.